Good day, students. In this lecture, we are going to learn the circular convolution property of DFT. See, this is a very important property of discrete Fourier transform. It's one of the important property of discrete Fourier transform. Let's look into the statement of it. It states that if DFT of x of n is x of k, then DFT of y of n, which is equal to x1 of n circular convoluted with x2 of n, will be equal to y of k, which is x1 of k into x2 of k. And here this star enclosed in a circle or n enclosed in a circle are used to represent the circular convolution operation. Okay. Now, from the statement of this circular convolution property of DFT, we can say that a complex mathematical operation called circular convolution is now being converted into a simple mathematical operation called product, that is multiplication. Is it not? That is the main advantage of learning the properties. We know that the formula for circular convolution is x1 of n convoluted with x2 of n is equal to summation m is equal to 0 to n minus 1 x1 of m x2 of n minus m. This is the formula for convolution. So if we look into this formula, if I want to perform the circular convolution in time domain, what are the steps that I have to do? I will be given two input sequences. The second sequence I have to shift, I have to fold it, and then it has to be shifted by n units. We have to multiply this folded and shifted sequence of the second sequence with that of this first sequence, and then you have to sum up all the samples. So this requires folding, shifting, multiplication and summation. 4 different mathematical operations are required if we perform the circular convolution directly using this formula in time domain. Okay. Now, if the same circular convolution is performed using DFT, if I take DFT of x1 of n convoluted with x2 of n, this circular convolution operation, which is very complex, is now being converted into very simple mathematical operation called multiplication. That is, we are going to take the DFT of x1 of n and then the DFT of x2 of n. We will get x1 of k and x2 of k. Simply we are going to multiply these two. We will get the result and take IDFT of this resultant sequence. We will take the result of circular convolution. So we can say that using this DFT, that is circular convolution property of DFT, the advantage that we get is circular convolution in time domain is converted into multiplication in frequency domain. This is the advantage that we get. Okay, let us look into the proof of this. And for proving the circular convolution property, we are going to consider this right hand side of the statement, and from this right hand side of the statement we are going to prove the left hand side. So let us take the RHS, which is y of k is equal to x1 of k into x2 of k. And we know that y of k is nothing but IDFT of y of n. We have to get this at our result, at the end of the proof, y of n. For that, we have considered the RHS of this equation. Now, we are going to find the IDFT of this y of k, so that we will get y of n. We can write IDFT of y of k is equal to y of n, which is given by 1 by n sigma k is equal to 0 to n minus 1 y of k e power j 2 pi by n kn. This is the equation for IDFT. Now if you look into this y of k, we know that y of k is x1 of k into x2 of k. So substituting y of k now, substituting y of k in the above equation, we will get y of n is equal to 1 by n summation k is equal to 0 to n minus 1 x1 of k into x2 of k, because y of k is x1 into x2, e power j 2 pi by n kn, right? And if you take this x1 and x2, x1 of k is DFT of x1 of n. So I can write x1 of k as, it is nothing but DFT of x1 of n, the formula for which is summation m is equal to 0 to n minus 1 x1 of m e power minus j 2 pi by n k m. If you look at this, we have already used the variable n here in this equation. That is why for finding the DFT of x1 of k, we have used a separate variable which is m. Okay. Same way, we can write x2 of k as DFT of x2 of n, the formula for which is summation L is equal to 0 to n minus 1 x2 of L e power minus j 2 pi by n k L. Again, to differentiate between the variables in the summation, for x2 of k, we have used the variable L. Now we have got x1 of k and x2 of k. We can very well substitute this x1 of k and x2 of k in the above equation. Let us consider this as equation 1. So, substituting x1 of k and x2 of k in equation 1, we will get y of n is equal to 1 by n summation k is equal to 0 to n minus 1. Then you have x1 of k term. So you have to substitute the formula for x1 of k, which will be summation m is equal to 0 to n minus 1 x1 of m e power minus j 2 pi by n km. Then you have x2 of k, the formula for which is L is equal to 0 to n minus 1 x2 of L e power minus j 2 pi by n k L. And in the equation of y1 of y of n, we had an exponential term which is e power j 2 pi by n into k small n. Okay, we have substituted x1 of k and x2 of k in equation 1. Now after this, if you observe the terms inside this, we can say that 3 exponential terms are there, and in all the 3 exponential terms, e power j 2 pi by n is common. So slightly we can rearrange the order of summation. So by rearranging the order of summation, we can write the same equation as y of n is equal to 1 by n summation m is equal to 0 to n minus 1 x1 of m, because this x1 has only m terms. So this can be written as a separate summation. Likewise, summation L is equal to 0 to n minus 1 x2 of L. So only this term is having L variable. So this can be separated. And if you look at all these 3 exponential terms are having the variable k. So all these can be grouped under a single summation like k is equal to 0 to n minus 1 e power minus j 2 pi by n km e power minus j 2 pi by n kl e power j 2 pi by n into kn. Now if you look at this, we can write it as summation m is equal to 0 to n minus 1 x1 of m summation L is equal to 0 to n minus 1 x2 of L, and the third summation can be written as k is equal to 0 to n minus 1 e power j 2 pi by n. Taking this e power j 2 pi by n as common, we can write the remaining variables as n minus m minus L into k. E power j 2 pi by n, k is common here. So we can write this n minus m minus L. Okay. Now we are going to simplify this summation. We are going to consider only this summation and we are going to simplify it. And for simplification purpose, we are going to make use of a formula which states that summation k is equal to 0 to n minus 1 alpha power k is equal to 1 minus alpha power n by 1 minus alpha. for alpha is equal to 1, the same as n for alpha, this is for not equal to 1. This is the formula that we are going to make use of to solve the summation which is inside the bracket. Okay. Now let us consider this. If we compare this summation k is equal to 0 to n minus 1 alpha power k with this term, we can say that this is same, and you can write this e power j 2 pi by n minus m minus l into k as the same thing can be rewritten like this also, right? Summation k is equal to 0 to n minus 1 e power j 2 pi by n into n minus m minus l the whole power k. Both are one and the same. Like this also it can be rewritten. Okay. By considering this, if we compare this equation and this equation, in the place of alpha we have this e power term. So we can write alpha is equal to e power j 2 pi by n minus m minus l. This is the value of alpha. Now let us consider n minus m is equal to l. Let us take l is equal to n minus m. If you substitute l as n minus m in the above equation, it will be written as e power j 2 pi by n minus m minus of, instead of l we have to put n minus m. It is minus of n minus m. It will become minus n plus m. This is alpha. Now if you look at this n minus n, m minus m will be cancelled. So this term becomes 0, which means this alpha becomes e power 0, the value of which is 1. Now substituting this alpha, we have taken alpha as the term inside the bracket. So substituting alpha as 1 to this summation, we will get it as summation k is equal to 0 to n minus 1 e power j 2 pi n minus m minus l power k, which is nothing but summation k is equal to 0 to n minus 1 alpha power k. Now since we have obtained the value of alpha as 1, this term becomes 1, that is alpha becomes 1. So it gets reduced as summation k is equal to 0 to n minus 1 power k. Now if you look into this formula, if you compare this equation with this formula, in the place of alpha we have 1. Whenever alpha is equal to 1, this summation gets reduced to n. So now this entire term, that is the third summation term, gets reduced to n. Okay. Now substitute this value in equation 2. Let's take this as equation 2 and this as equation 3. Now substituting 2 in 3. Okay. Substituting 3 in 2. What we'll get is y of n is equal to 1 by n summation m is equal to 0 to n minus 1 x1 of m. It will be as such. Summation l is equal to 0 to n minus 1 x2 of l into this entire summation has now been reduced to n. So I can take it as n. Okay. Now this n and this n will get cancelled. And the equation becomes summation m is equal to 0 to n minus 1 x1 of m summation L is equal to 0 to n minus 1 x2 of, we have assumed L as n minus m. L we have taken it as n minus m. Okay. So here again I can write, instead of L I can write n minus m. We are left with these two summation. Now if you look into this summation, we can actually neglect this. The reason is this summation exists from 0 to n minus 1, right? For L is equal to 0 to n minus 1. And now this term within the summation has not got any L value. And also we can say that this summation exists only for L is equal to, it exists only for L is equal to m. For L is equal to n minus 1. So this is going to exist only for one term of L, which is equal to n minus 1. So this summation can be neglected. It can be very well removed because L is having, it's not going to have a sequence of values from 0 to n minus 1. Instead, it is going to have only n minus m value. Okay, so we can neglect this summation and the equation for y of n becomes summation m is equal to 0 to n minus 1 x1 of m into, sorry, you will not get the summation, into x2 of n minus m. Now this equation is nothing but the formula for finding the circular convolution of x1 and x2. So we can write this as, this is nothing but x1 of n circular convoluted with x2 of n. Okay, so we have taken the right hand side of the equation and we have proved that x1 of n minus x1 of n convoluted with x2 of n is x1 of k into x2 of k. We have taken this right hand side of this equation and we have obtained the formula for convolution at the end. So we can say we have proved the property of convolution.